So today we are dealing with the geometric Hahn Banach theorems. So the setting that we will first consider is you start with a convex K, which contains at least one interior point, and then you choose a point Y, which does not belong to K. And then the idea of the geometric Hahn Banach theorem is that you can separate K and Y. And we will see that the proof relies on an application of the Hahn Banach theorem that we studied in lecture 1. So let's start with the definition. So first, a quick reminder. So we can define what's a convex when we have a linear space. And so the definition is written here, definition 2. It says that if X and Y belong to K, then the whole segment has to be included in K. And a segment writes as if X and Y belong to K, Tx plus 1 minus Ty with T between 0 and 1 has to belong to S. Next, we say that, so in general, this is, you define an interior point by means of a ball and with a distance in a metric space. But here, right now, we don't have metric space. We just have a linear space. And we can also define an interior point by saying that point X is interior to S if there exists epsilon greater than 0, such that as soon as T is less than epsilon, then X plus Ty belongs to S for all Y in X. So once we have clear definitions of all those things, which with you are familiar, but here the interesting point is that we didn't define a metric. I find it very, very interesting. But okay. And this is the first theorem, which says that exactly it corresponds to the picture. So you consider a linear space over R. K is a non-empty convex subset of X, and the assumption is that K has at least one interior point. So next, if Y is not in K, then there exists a linear functional L from X to R such that L of X is less than L of Y for all X in K. Furthermore, you have a strict inequality for all interior points X of K. So since you have a linear function, yeah, so, and we did the Hahn Banach theorem, it's good to wonder if we can apply the Hahn Banach theorem to prove that. But first, before going into that, we will need to define the gauge function. So what's a gauge function? So we start with a subset K, and we assume that 0 is an integral point of K. Then the gauge of K that we denote by Pk is the real valued function defined on X by Pk of X is the inf of all the B, the positive B, such that when you divide X by B, you belong to K. Okay. And since 0 is an integral point, you always, for each X, you have a finite B such that X divided by B belongs to K. And you take the inf of that. All right. So first, you have this lemma. In fact, Pk is positively invariant and subadditive. So we're getting closer to the assumptions of the Hahn Banach theorem. So we're going to prove that now. So the first point, when you say that X divided by B belongs to K, is the same thing that saying AX divided by AB belongs to K. So when you take the inf of the B such that X divided by B belongs to K, it will be the same value that taking the inf over the values AB such that AX divided by AB belong to K. So since the sets are the same, you got this equality, which proves that Pk is positively invariant. Next, subadditivity. So now assume X divided by B and Y divided by C belong to K. We're just doing this trick. You consider X plus Y divided by B plus C. And you just here you split the sum. So you got X divided by B plus C plus Y divided by B plus C. And you multiply and divide here by B divided by C, C divided by C. So this is so now the point is that X divided by B belongs to K, Y divided by C belongs to K, and B divided by B plus C plus C divided by B plus C equals 1, which means that since K is a convex set, this sum here belongs to K. So because this quantity belongs to the segment X divided by B plus Y divided by C. Okay, we could draw a picture here. Assume you have X here, you have Y here. So if you have X divided by B, here you have Y divided by C, then all the segment here belongs to K. Okay, so now since this now belongs to K, this means that B plus C is you deduce that Pk of X plus Y is less than B plus C, right? By definition of the gauge. All right, and that's right in here. And now to complete the proof, you just some details. So you took a sequence Bn and a sequence Cn that converge respectively toward pk of x and pk of y here. And so from the previous computation, you know that this inequality holds. Now you take the limit and you obtain what we want, right? And that's it. Okay, so we are going to prove that there exists a linear functional L defined on a subspace y of x such that L of x is less than pk of x for all points in y. So now from the assumption in the theorem 4, we have one y, we have y that does not belong to k. And so let's say that we set L of y equals 1. But now, since y, so since L is a linear function, if you set L of y equals 1, you define L for all ay. So if L of y equals 1, then LAY equals ALA equals A, actually. All right, but you define your L all over the subspace defined by AY. Okay, now since y does not belong to k, if you have y divided by b which belongs to k, necessarily b must be more than 1, right? So taking the inf on all of those b to get the pk of y, you obtain that pk is greater than 1. Okay, so that's good because that says that L of y is less than pk of y. And since pk is positively homogeneous and L of y is linear, you have this inequality, in fact, for all y's in the subspace AY, which appears here. So that's good, because now we can apply the Hahn Banach theorem. Yeah, because I forgot to say for negative A, but this is direct, okay? Because pk is positive, and if A is negative, then necessarily you have LAY less than pk of y when A is negative. Okay, now I can apply my Hahn Banach theorem. And that's it. So that's it. If I apply my Hahn Banach theorem, I got that I can extend L of x equals pk of x for all x in x. And now if x belongs to k, you have that pk of x is less than 1. So you obtain that, and this is L of y. So combining here with that, you have the conclusion of the theorem 4, which is L of x less than L of y. Now, the strict inequality comes from the fact that if x is an interior point of k, then when you take the inf, you will have pk of s is strictly less than 1. And since you have this inequality, this gives you the strict inequality when x is an interior point of k, right? So next we consider this exercise. So prove that pk of x is less than 1 if and only if x is interior to k. So we have already seen that if x is interior to k, then pk of x is less than 1. Just think about it. We already saw that it's direct. However, conversely, if pk of x is less than 1, then x is interior to k. This is not direct. Let me draw something here. Actually, I'm gonna take that and so we have our vector space, and we have here the 0, and you have here x. So we assume that pk of x is less than 1, which means that you have some b such that x divided by b belongs to k, with b less than 1. Okay, which means what? Which means that from here I will draw a line, and I can come here. This one belongs to k. So here I have x, and here, let's say I have x divided by b. Okay, the point is what now? We know that 0 is interior to k. So you have, for some epsilon, you have here, it's clearly a ball. Even I didn't define it. But from the definition of an interior point, you have here some set which belongs to k, and since k is convex, you have all this object. I can draw here because it's convex. So this belongs to k, and all this belongs to K. So next, I have all these points in yellow that belong to K, meaning that I can also define a small set such that X plus some epsilon Y, it's T belong to K for all T less than epsilon and for all Y belong to X. Yeah, so to write it now to Hahn, you can take the negation, say, assume that now X is not interior to K, and then with this construction, you will find a contradiction. So try to do review this exercise at home and write it down. So yeah, try to understand that. All right, let's come back to this. All right, so now we will end the session with this theorem 5. So now so theorem 5 is what now? Instead of one convex, you have two convex, H and M, which are disjoint subsets of X, and you assume that at least one of them has an interior point. Then you can separate H and M by a hyperplane, L of X equals C, which means what? Which means that there exists a linear functional L and some number C, such that L of U is less than C is less than L of V for all U in H, for all V and M. And just a quick idea about the proof. What we are going to do to prove theorem 5, we are going to apply theorem 4. So we need to, from the two convexes H and M, you need to construct a single convex K. And that's what we do. So you construct K as this, all right? So K is the points of X such that you can write it as X equals U minus V, U in H, V in M. Now, what we need to verify is that there is some point which doesn't belong to K. And we can say that 0 does not belong to K. Why? Because X equals 0 if and only if U equals V, but H and M are disjoint, so there's no point in X such that it belongs to U and it belongs to V. It belongs to H and M, so you cannot cancel U minus V, right? Next, you also need to prove that K has an interior point. So without loss of generality, you can assume that H has an interior point, and if H has an interior point, then also K, right? And so then you apply theorem 4 to that. And applying theorem 4 gives you that L of u minus v is greater than L of 0. So yeah, my 0 is my y, but L is a linear function. So L of 0 is 0, which gives you L of u. Actually, it's a less here. If it's a less. Here it's less. There's a typo here, and so you have L of u is less than L of v. And so yeah, that's the end of the proof, because now you can take some C, such that this thing holds, and that's it.